Saxon Advanced Mathematics, Lesson 104. This has been a week of digging up some old lessons and taking them in some new directions. This time we're going to talk about our friends, the arithmetic sequence and the geometric sequence, and we're going to bump up our understanding of what we can do with those a little bit more. Those lessons go back, I know that arithmetic one was back in the 80s. So I'm going to review everything that we've learned because it's been a hot minute. So let's talk about what an arithmetic sequence is, because that's something slightly different. This is what we called it when we studied it before. We called it an arithmetic sequence. And we learned that it's something that we study. I'm trying to find a nice straightforward one for you here. 1, 2, 3, here's one with 8 terms. Let's use this one. Remember, we would circle this information because this represents the terms of the sequence. The first term we referred to as A1. Then with each additional term, we could write a pattern for that. I'm going to write them all down, and you'll be able to figure out the pattern probably quite easily. We realize that there's a common difference and that with each additional term, we're adding the common difference one more time. We refer to the common difference as D. Plus 2D. I'm going to go down just so I can squeeze everything in. A1 plus 4D, A1 plus 5D. All right, and we recognize that the number of times that you multiply D for each term is one less than the number of the term. So what I'm saying, for example, here is for the 5th term, we multiply the common difference times 4, because for the very first term, we don't add the common difference. So that's why it always lags one behind. But A1 is the original amount, and in this case we can see it was 11, and D is what we call the common difference. Now, that we all knew. We knew how to do that, and we did a bunch of problems where we get some information maybe about the 8th term and the 2nd term, and we'd have to find out the original amount. We did a lot of different problems playing around with this. Today we're going to introduce this new idea, which is called the series. And the idea here is that a series is when you add all the terms of a designated sequence. What does that mean in proper English? It just means you add them all up and get the total. And you get to say, you know, what's the original amount, what's the common difference, and how many terms, right? For a series, you have to define all those things so that you have a limited number of things that you're adding. But a series represents the total. You just add them all up. Now, the problem is that that's really annoying. Do you want to add all those numbers up? I do not. So what we do is we look at the pattern of how those numbers flow, and we will write a formula that will allow us to find the total of the series without having to create the entire sequence and then do all that addition. Here's what I want you to notice. I'm going to rewrite the sequence down here because I'm going to draw on it. Okay, there are 8 terms, and then 11, what we're going to do is we're going to start by adding the first and last terms of the sequence. 11 plus 32. That adds up to 43. Okay, now let's add the second to the last, the second from the first and the second to the last. 14 and 29. What does that add up to? 43. Huh, all right. We'll go in another, right? So now we're third from the beginning, third from the end. 17 and 26. And please don't be shocked when we do the last one, 20 and 23. That's a very interesting thing about a sequence, is that it will yield this pattern of pairs. And we can use that to write the formula for the series. What we realize is that for every number of terms in here, we had 8 terms, and when we paired them off, we got if you take the first and the last number and multiply it by 4, right? Because it took 2 terms. There were 8 terms in all. You have to pair them. So that's 8 divided by 2 gives us 4 43s. And we got the first 43 by adding the first and the last. So we can write that. I'm going to write it. We're trying to create a formula is what we're doing here. So let me write that. We added the first term and the second term, and we got that 4 times because we had 8 terms, but we were adding 2 together, so we have to divide that by 2. That would give us the sum of all 8 terms, which is exactly what a series is. So that means we can say that the series, the total for any number of terms, you take the number of terms, you divide it by 2 because you have to put them in pairs, and then you add the first term plus the last term. Oh, I'm sorry, this is wrong. Last. Glad I caught that. You were probably wondering, what is she talking about, the first and the second? No, it's the first and the last. And we define that as a to the n, right? Because n is the number of terms. Okay, so in our case, we used 8. The total for all 8 terms is you take 8, you divide it by 2, that gives you 4 pairs, and then you add the first and the last to get the number, because what we found is that is one way to get the number, and that's the easiest way to define it for our formula. It also works if you take the second and the second to the last, or the third and the third to the last, or the middle. Now, one thing that is potentially confusing, but spoilers, it's not, is that we think, okay, well, this worked out really great when we had an even number of terms, but what if we had an odd number of terms? Then it wouldn't come out even. We wouldn't have a pair for every single one. Wouldn't that screw it up? No, it does not, because what we're going to do is, like, say this was 9 over 2, which is going to be one of the examples, has an odd number. We would just take half of this again. So I don't know if that makes any sense to you, but trust me, it works out for even or odd. Number of terms. So that's happy news. We don't have to worry about it being different. All right. So let's practice using this formula in an example. An arithmetic sequence has a first term of -10. Oh, I know how to write that. And a common difference of +20. Use the first 4 terms of this sequence to write a series and develop the formula for the sum. Then use the formula to find the sum of the first 11 terms. Okay, so first we're going to use n equals 4. And then after we figure out the formula, we'll use n equals 11. Now, here's the thing about John. He thinks that at the level of math we're studying now, just being told, oh, look, here's a formula, and being asked to plug numbers in, he thinks that's beneath us. He thinks we're better than that. So he's always asking us to redevelop the formulas. Even though we know what the formula is, he's asking us to kind of do the spade work, if you will, of redeveloping it every time. Okay, fine, we'll do that. It's not that bad. So here's what we've got. First, we're going to use 4 terms, right, to develop the formula. And so we know that the original amount goes here, -10, and then we start adding the common difference, right? We add it once and we get +10, and then we get 30, and then we get 50, right? Okay, and then we start noticing, and we're going to want to add this all together, right? Because that's what a series is we add those all together. We want to find an easy way to add them. So we start with the first and the last. -10 and 50 gives us 40. And quickly we see, okay, well, the second one is 40 also. So we know that the way to get the total number for this one, which honestly I wouldn't mind adding in my head, and we'll do that to check our answer. We can take the number of terms that we have, which is 4. We divide it by 2 because we're making them in pairs. And then we're going to multiply that by the value of one of the pairs, which is the first. So we call it A1 plus the last, which in this case is A to the 4th. So that's how we would find the total. And so we know if we plug in the numbers for hours, it would be 4/2 times -10 plus 50. This is 40. And if we multiply that by 4/2, let's see, this would reduce to 2/1, right? And then it's just 40 times 2 is 80. Let's double check. These two cancel, and there's the 80. So we just did the straight addition, and we found out that our formula works. Now, because in our example, n was equal to 4, we can rewrite this as saying the series for any number of terms equals the number of terms divided by 2 times, and we wrote this with a 4, but we're going to change that to an n because we want to have a formula. This is the formula. It's exactly, well, it's kind of hard to show you because, here, I'm trying to show you both things without a lot of other information. This equals this. We redeveloped the formula based on these 4 terms, but we got exactly the same thing. Okay, good news. Now we're going to use our redeveloped formula to solve for a series of 11 terms with the same original amount and common difference. So we don't have to draw this all out. Now we can use this formula that we just developed. So the total for a series of 11 will equal 11/2 times the first amount, which is -10, plus the amount of the 11th term. We don't have the 11th term, so we're going to have to figure that out. A to the 11th, well, we know the formula for that. You take the first one, and then you add the common difference times 1 less than the term. Remember, that's what we looked at here we notice that, let's look at this one. In the 7th term, we multiplied the common difference times 6. It's always one less, and that's because here for our first term, we don't have a common difference at all. All right, so the number of times we're going to multiply our common difference is going to be one less than the term. This is the 11th term, so we multiply it by 10. Now we plug in our values. A to the 1 is minus 10, and then we're going to add that as 6 times 20. Right, makes sense? I'm just plugging in what we know. We have our A1 and our D up here. Okay, then we just simplify. This is 120, right? So A to the 11th equals 120 plus minus 10. Wait, I see what I'm doing. I'm doing this wrong. I'm using the 6, but that's not right. It's 10 times the common difference. Where did I get the 6? I don't know. The common difference is 20, and we're multiplying by 10 because we're trying to find the 11th term. So that means this is 200 minus 10. Sorry, my brain went sideways there. Make sense? So we determine here that the value of the 11th term is 190. So now we can use that in our calculation right there. Okay? This was very straightforward. Where did the 6 come from? I made that up terribly, didn't I? Okay, so now we are ready to add these two together, because we're just simplifying this, right? So this is 180. I'm going to cancel this against the 2, and this will become 90. So it's 11 times 90. So the total we get, if we run this arithmetic sequence out to 11 terms and then add up all the pieces, the total will be 11 times 90, which is 990. And that is the correct answer. Yay! All right, so we have a formula, it works, we know how to develop it from our specific example. So, John is happy that we're having so much fun. All right, that's the arithmetic sequence. That, remember, is where we are adding a number each time in the sequence. Right, we were adding an additional, what were we doing in this one? We were adding 3, weren't we, with each additional one. A geometric sequence, I'm going to show you one in just a minute. A geometric sequence is when we are multiplying, not adding, but multiplying. So it's kind of the same idea, but it's a little bit different. I'll refresh our MEMS. We're going to do the very same thing. We're going to learn how to develop the formula, and then we're going to practice developing the formula in a super nifty example. So let us start this time not with using numbers, but with just using letters. Developing this formula is a little bit crazier. So buckle in. This is the geometric series. Again, the only difference between a sequence, which is what we've called it before, and a series is that for a series, we add together all the elements of a certain number of terms of the sequence. So it's trying to find the total. Okay, so let's look at what that was like. We're just going to use letters, but again, I think you'll recognize it. Okay, so let's say that we're going to do 1, 2, 3, 4, and then we're going to leave the end of our sequence undefined so that it will work for anything, right? So this will be a to the 1. Then what we do for the second sequence is we multiply it times r, which is what we call the common ratio. It's the multiplier. And just like we saw with the common difference, the number of times we use the multiplier, which in this case is expressed as an exponent rather than a coefficient, that number always lags one behind the number of terms. Technically, we can call this r to the first, right? Because our first term doesn't have a common ratio. So every time we multiply the common ratio, that number will be one less than the number of terms, okay? And that's going to be important to us. So this one will be a1 times r to the n minus 2, right? Because it's one less than that. And then this will be a1 times r to the n minus 1. And I'm putting those dot, dot, dots in there to show there could be more terms. All right. So we would say that the series of n terms equals, and I'm just going to write this all again. The series is when we add them all together. Oh, I forgot. I did that wrong. Boy, I am just making the crazy little mistakes. I suppose catching the mistakes is less of a problem than the ones I don't see. Plus a1r to the n minus 2 plus a1 to the r n minus 1. All right. All I did was copied these, hopefully correctly, and put add signs between them, because that's what a series is the addition. Now, we're going to do something weird. We're going to take this as an equation, and we're going to multiply every term in the equation by r. That's weird, right? Okay, we'll do it. So, I'm going to call this equation A, and this new one that we're creating, I'm going to call B. R times Sn equals, and look what I'm doing. I'm bumping up the number of r's in each one of these, aren't I? And this will become instead of n minus 2, since I'm increasing the number of r's, it'll be n minus 1. And then this one, when I multiply it by r, it'll be a1r just times n, right? Because I'm adding an r each time. Okay, so this is weird. Why did I do this? Well, don't worry. Now, the second thing we're going to do we're going to take equation B, and I'm going to write equation A here. We're going to multiply equation B by minus 1. We're going to turn all of these negative. Are you ready? And then we're going to add to equation A. All right, so we're going to be offsetting these. Do you remember that lesson way back at the end of Algebra 2 where we showed that numbers with non-repeating decimals do actually cancel out? It's a weird calculation we did where you write out all the repeatings and then you set it up so that they will cancel. This is kind of like that. We're going to make most of this cancel, and what we're doing is we're setting up our equation B so that it will cancel nicely. Okay, so now what we're going to do is turn all these positives into negatives. I'm going to write it over again. So here's our equation B. Don't worry, we're getting close to the satisfying part. I'm just copying everything down with minus signs in front of it. Okay, so there's this equation that has already the extra r's, then I'm multiplying it by minus 1. We could have multiplied it by minus r in the first place, but John was trying to let your brain keep up, and I agree. I think that that's too much. But now I'm going to copy back equation A so that we can have them close together. All right, now we're going to add them. This is not going to subtract because this one has an r and this one doesn't. So this is going to become Sn minus Rsn. And now look what's going to happen. This A1 stays. There's nothing to cancel that out with. But once we start getting the r's involved, that cancels, that cancels, that cancels. We haven't written this out, but we could easily, because we had dot, dot, dot in here, right? We could easily write plus a1r to the fourth to help that cancel. We didn't write a1r to the n minus 2, but we did put the dot, dot, dot. So we can write that in, a1 r to the n minus 2. We can put that in the sequence up here. That will allow that to cancel. This cancels, and we're left with this at the end. All right? Don't let this mess with your head too much. We just didn't write down every single term, but we can add them back in if we want, because they exist. So what we're left with when we cancel out all this stuff in the middle is we're left with this on the left, which was this piece and this piece, and it's equal to a1 minus a1r to the n. Whoa, so much better, right? We got rid of so many terms. Now what we can do is factor a little bit to clean this up. So I'm going to factor this. I'm going to pull an Sn out, and that will leave me with 1 minus r. And then on this side, I'm going to pull the a1 out, and that will leave me with 1 minus r to the n. All right. And then for my last step, because I want this by itself, so I'm going to divide by 1 minus r. We can put this in parentheses or not. I guess I would rather overdo the parentheses. But I'm dividing that away, right? So this cancels. So the final version of our formula, and we're there now, is that to find a geometric series, you use this formula. I'm going to copy it to the next. Well, here, let's just do this. I wanted it to be pretty for you, but this is pretty good, right? There is that puffy cloud of heavenly knowledge. This is what we can use to find the series, the total of a geometric sequence of a defined length. We calculate each one of those terms, and then we add them all up. We don't have to do the work. We can just use this formula. Oh, Heavenly Father, let's go to the next page. Let's rewrite the formula, okay? So to find the total of a geometric sequence, we take the first element, we multiply it by 1 minus the common ratio raised to the power of the number of terms. Just looking at this, I can't explain to you why this works. It's only by going through this long process that we can say, yeah, it does algebraically compute out to this value. Okay, let's use it in a problem, shall we? We went to all that work. The least we can do is see how now it's going to save us time. Develop the formula for the sum of the first n's terms in a geometric series. We just did that. and use the formula to find the sum for the first 9 terms, so n equals 9, in a geometric series whose first term is -8 and whose common ratio is -2. All right, now, John may think that it's boring for us to just plug and crank numbers through a formula. I'm not mad about it. I'm perfectly happy to do this, and I don't think that it's like, less of me. So there's our formula. There are our values. Let's put them in. So to find the series for the total of 9 terms, we'll take the original amount and we'll multiply that of 1 minus the common ratio. Now, I highly recommend that you use parentheses carefully. This is -2 to the 9th power. Oh, wow, okay. Well, we'll figure that out. And then on the bottom, we'll have 1 minus -2. All right, so now we have to simplify. How do we simplify -2 to the 9th power? Well, if you've ever played that game, it's a phone app. It's called 2014, and it was really popular, I don't know, maybe 5 or 8 years ago. So you guys were probably too young for that. But it's a really cool game because you're combining tiles of 2s to make powers of 2. And every time you combine them, you make a higher power of 2. So it's really great practice. So let's just do this. 2 times 2 to the first, 2 squared, 2 to the third, 2 to the fourth. I'm just gonna make a little chart here. You can probably leap into this at some point, but I'm just gonna start from the beginning. 2 to the 1 is 2. And then we just multiply by 2 every step of the way down, right? 16, 32. We double it, 64. We double it, 128. We double it, 256, and we double it, 512. I haven't played that game in a while. It's making me hanker for it. Okay, so 2 to the 9th is 512. However, it's also a minus, so we know it's going to stay minus. So this becomes -512. I'm going to rewrite the minus sign just because it looks like I crossed it out. So when I put these two together, everything in this parentheses comes down to 513. Does that make sense? 1 plus 512. Whew. Okay, so this is 513. We need to multiply that by -8. So 513 times 8. I know it's going to be minus 24. So this is the numerator. With this minus sign, this one stays. And the denominator is 3. Does 3 go into 4,104? Let's look. We add the digits, 4, 5, 9. Does 3 go into 9? Yes. So 3 should go evenly into this. And let's do the long division. You're doing it too, right? So what we find is that if you create a geometric sequence of 9 terms where the original amount is -8 and the common ratio is -2, and you add those 9 terms together, the number that you will get is -1,368. And that's the right answer. Now, the next question you have to ask yourself is why? Why would we want to do that? I don't have a good answer for that. Again, we're learning tools that are a part of the bigger calculations, but as long as it makes sense to you how to do this, that's what matters to me. I want you to redevelop this formula every time it comes up in your homework once a day. You don't have to redevelop this formula. And by that, I mean go through all these steps. You don't have to do that multiple times a day, but I want you to be able to do it fairly easily. It's like Pascal's triangle and the pattern of exponents that we did in that previous lesson. I want you to be comfortable with developing them, even if you don't do it. Like, it takes a lot of time. So do it enough so that you're comfortable, but nothing more than that. Okay, there is our formula. On a test, though, I would expect you to be able to develop that, so make sure you can. Maybe we'll do it one more time. Well, I don't want this video to take forever. That's what I always run up against. 104.3, they're long enough as is, right? And I don't want people dropping out in the middle of the video because they're losing their mind. Find the sum of the first 10 terms of the geometric series in the preceding example. Okay, so what we're saying is use the same value for A1, which was -8. Use the same value for the common ratio, which was -2. And do it for this number of terms. Okay? So we need our formula again. The total of the number of items in the series is equal to the first one and that's the formula. Make sure you memorize that. Okay, so for 10, we take -8 and we multiply it by 1 minus and we create parentheses because we have a lot of minus signs flying around. The common ratio, -2, raised to the power of 10. All right. Yeah, last time it was 9. Okay, and then this is all going to be over 1 minus r, which is -2. Okay, so now we're going to simplify this. We always start in the middle, right? We learned that way back in pre-algebra. Always go to like the inner core of the expression you're trying to simplify. Now, we figured out last time that 2 to the 9th power was 512. So we know that 2 to the 10th power is going to be double that, 1024. 2 to the 10th equals 1024. So that's going to go here, but notice it's minus. So I'm going to write it again, just so that we're clear. Right? It's 1 minus okay, it's -2 to the 10th power. The 2 goes along for the ride, right? It was part of the package that we were squaring. So because we have an even number of 2's, this becomes positive. So now it really is, it's going to be -8 times 1 minus that. So it's going to be -1023, right? That's a big number. And then we're going to divide it by 3. So let's multiply. And I would prefer you to do these calculations by hand. Don't use the calculator. They're not that hard. And we have been relying on the calculator a lot more in recent lessons. So let's make sure we can still do this. 8 times 3 is 24. This is 16, 17, 18. 0, 1. 8, 1, 8, 4. And then we're going to see if we can divide that by 3. Let's see, 9 and 12 is 21. 21 is divisible by 3. I added these digits, right? 8 plus 1 plus 8 plus 4. They add to 21. 21 is divisible by 3, so that means this number will be divisible by 3. Okay, so let's divide by 3. I'm going to cross this out and write my answers up here. 3 into 8 is 2 times. 3 into 21, oh, that's 7. Bring down the 8. Oh, it goes twice into that. So our final answer is that the total of the first 10 terms of this sequence will equal, where'd it go? Here, 2,728. And that is one of the things about geometric sequences, right? Is they swing from negative to positive. So we went from the total of the 9 terms were equal to that negative number. So when we add in the 10th term, the total swings way back up. This is the right answer. And now I've told you all you need to know to be dangerous about arithmetic series and geometric series. Whew, that was a good one. Thank you. Goodbye.